The examples of induced EMF analysed in the last sections were of two types, involving either a conductor moving in a magnetic field or changing flux through a stationary conductor. Another example of the second type, where you've got the flux changing, is shown here, where a solenoid is encircled by a conducting loop with a galvanometer in it. So we've got this galvanometer enabled us to measure how much current is flowing. A current I in the winding of the solenoid sets up a magnetic field B. So we've got this current here, it's running round, and it sets up a magnetic field vector B along the solenoid axis along here, and there is a magnetic flux. So the flux is this across the whole area, so we know the flux across the whole area. Sorry, that should be the magnetic flux, which is BA. So there is a magnetic flux, which is B times A, through the surface bounded by the loop. When the current I changes, causing the flux to change, the galvanometer indicates a current in the wire during the time that the flux is changing. The associated EMF is equal in magnitude to the time rate of change of flux through the surface bounded by the wire. Furthermore, the directions of the induced EMF and current are given by the same sign rule described before. If we take the surface element, dA here, to point in the direction of B, so if we're assuming that that's pointing in the direction of B here, and if I is increasing, the flux by dt is positive, the induced current is in the counterclockwise sense around the loop, as shown. Thus we have the EMF equals minus the flux by dt. This equation is, again, it's Faraday's law. We emphasise once more that it's valid for flux changes caused by motion of a conductor in a magnetic field and by magnetic field changes in the area bounded by a stationary conductor. So here's an example. Suppose this long solenoid here is wound with 1000 turns per meter, and the current in its windings is increasing at the rate of 100 amps per second. The cross-sectional area of the solenoid is 4 centimeters squared, or 4 times 10 to the minus 4 meters squared. The magnetic field magnitude inside a solenoid at points not too near its ends is given by, so this is the equation for a solenoid here, which I think we went over before. So I'm just stating the equation here. The magnitude of the magnetic field B is given by magnetic permeability times the number of turns times the current. So the flux there in the solenoid then is flux times BA, where B is given by this, so we can just replace that with mu naught NIA. Now the rate of change of flux is d flux by dt divided through by dt here. We're given di by dt was 100 amps per second. We know what the A is, it's 4 times 10 to the minus 4, and we know what the permeability is, that's 4 pi times 10 to the minus 7. So we plug all those in and we get 16 pi times 10 to the minus 6 Webers per second. Given that we've got this now, that's also equal to the EMF. The magnitude of the induced EMF is then simply 16 pi times 10 to the minus 6, and that is equivalent to volts. The EMF for this loop